Welcome everyone to lecture 24. Today we'll be talking about approximation algorithms. So we talked last lecture, if you remember, about problems that for the most part are very difficult to solve. There aren't any algorithms that we know of that can solve them in a fast time, in a polynomial time. Today we're going to talk about what we do and how we deal with that. We're going to start by reviewing what we talked about last lecture, making sure that we're all on the same page in terms of some core definitions. And then we'll look at some NP complete problems. In other words, we're going to look at some problems that are right now very difficult to solve, very difficult for computers to compute. And then we'll just end from there. All right. So this is the last new material we'll cover. From here on out, there's going to be a review on exam 3. So you definitely want to show up for next week's lectures. It's basically as mandatory as this week's lecture because we'll be talking about how to study for exam 3, what's going to be on the test, what I'll ask, and go through some practice problems. Okay. So let's dive right into it. Today, just as a reminder, we think about algorithms and problems sometimes in terms of complexity classes. So there's a bunch of different problems that we've talked about in this class: sorting problems, problems on how to print trees out in a certain order, problems on how to find the shortest path between A and B on a graph, finding the minimum spanning tree. We looked at a fair amount of algorithms, and each problem has more than one algorithm, right? There's more than one sorting algorithm. There's more than one way to print out a tree. There's more than one way to find the distance between A and B in a graph. And nearly all of the problems we've seen are tractable in the sense that the algorithms that are associated with them have efficient algorithms. The algorithms that are associated with them are efficient, right? They can run in like maybe O of 1, O of n squared, something around those lines that makes it really an algorithm we can actually use in real life. However, there are problems for which we don't have any polynomial time algorithms for. In other words, the best algorithms we have to solve those problems are exponential, and we call those types of problems intractable problems. In real life, if you're trying to find or solve one of these problems, you realize that it's intractable, then you know that you want to avoid trying to come up with an algorithm that's fast that gives you the optimal solution. And instead, you want to find maybe a way to approximate a solution because that's probably faster. You're not going to get the best answer, but you'll certainly get an answer that's good enough for all intents and purposes. And that's what we're going to look at today. So if you remember, the first two complexity classes we cared about from last lecture were P and the complexity class NP. P is the set of all problems that you can solve within polynomial time. So in other words, every problem that has an algorithm that can run in maybe, O of n squared, O of n to the power of 10, O of n log n, O of 1, all of those algorithms belong in one bucket that we call the complexity class P. NP is the set of all problems that can be verified in polynomial time. In other words, if we have some problem where we can get an example of that problem and get a solution for that example, we can test to see if that solution works and that it is a correct solution for that problem in polynomial time, right? So all the problems that can be checked in polynomial time belong in the complexity class NP. Now, some problems in NP, we don't know if they have a polynomial time solution. In other words, we only have algorithms that run in exponential time to solve them, which is slow. And the question, is P equal to NP, is essentially asking, which world do we belong in? Do we belong in the world where every problem in NP is also in the complexity class P? In other words, for all the problems we can check very quickly, whose examples and solutions we can verify very quickly, can we also solve those problems very quickly as well, right? And we don't know. There are two worlds we can live in. We can live in world 1 where P is not equal to NP. That is the world that we currently assume we're in. And it's the world that we think exists problems that are in NP that are just always going to be hard, right? So the problems in NP complete are the problems that have exponential time algorithms, right? So all algorithms that live here, or rather all problems that live here, have exponential time algorithms. And this is assuming we live in a world where P is not equal to NP. Now, if we live in world 2 instead, where P is equal to NP, then that means that the problems that we previously thought were very challenging, like breaking into someone's Facebook account by cracking their password using by somehow decrypting the password, that actually turns out to be easy. Or like, for example, protein folding, which we think currently will take exponential time in the best algorithm we have will take exponential time. That turns out in world 2 to be actually easy. We can do it in polynomial time. In other words, we can use like a normal computer and run it for a normal amount of time, and we can get a solution that will end up inevitably curing cancer. That's the hope, right? We don't know if we live in world 1 or if we live in world 2. Everyone is assuming we live in world 1, but we might actually live in world 2. No one knows for sure, right? No one has proved one way or another. So that's the worlds as we know them. And as you see in these pictures, there are 2 other complexity classes that are labeled here. This idea of NP hard, which are problems that are just very, very challenging to solve, problems that are at least as hard as the hardest problems in NP, and NP complete, which is like the overlap between the class NP and the class NP hard, right? The class NP complete here is either this part that I've highlighted in pink or this part I've highlighted in pink, depending on whether or not we're in world 1 or world 2, right? So NP complete can look like 2 different parts of this graphic, depending on whether or not P is equal to NP, right? So in the world where P is not equal to NP, then the hardest problems in the class NP are exponential. They have algorithms that run in exponential time, and they're a separate entity, a separate space from the problems that can be solved in polynomial time, right? Because obviously if these problems can be solved in exponential time only, then they would be separate from the problems that actually can be solved in polynomial time. Now, in world 2, where P is equal to NP, we say that all the problems that can be solved in polynomial time are also all the hardest problems in NP, which are also all the problems in the class NP, right? So NP complete is the same as NP, which is the same as P in the world where P is equal to NP. This complexity classes, they all collapse into one big circle, right? And NP hard is a complexity class that will circumscribe or like envelop all of those types of problems. Okay, so this is review. If you feel like anything I just said is still very confusing, please go back and watch the video that we had for the last lecture. This will come up on the exam. This is something I expect you to understand. If you have any questions about this diagram, please ask now or ask in office hours or ask on Piazza. It's super important for you to feel good about this. We'll go over some review next week, but you should try your best to learn this as early as possible. Okay, so as we mentioned, there were 2 other complexity classes that we want to make sure we have the definition for. The hardness of a problem, before we talk about that, the hardness of a problem is defined by how slow is our best algorithm to solve the problem, right? So in other words, if I have a problem whose best algorithm is going to take exponential time, then that's a pretty hard problem to solve, right? A problem that is hard, a problem is hard when the algorithm to solve it is really slow. In short, NP hard is defined as the problems that are at least as hard as the hardest problems in NP. And NP complete are problems that are NP hard, but still in NP. In other words, the hardest problems in the class NP. And as far as we know, the best algorithms for each problem that is NP complete is exponential in the worst case. So the best algorithms that we have in NP complete in that set of problems are exponential, as far as we know right now, right? This is assuming we live in world 1 is the kind of caveat that we have here, right? And so today we're actually going to go ahead and take a look at what to do in this situation. When we have NP complete problems, that means these problems are really hard to solve right now. They only have exponential time algorithms, and that means anytime we have a large instance of this problem, for example, we have a large graph for minimum vertex cover, it's going to take a long time to try to find the absolute best solution for it, to find the minimum set of vertices that we need in order to touch every single node, at least at one end, right? There are really 2 ways we go about solving this. Like sometimes we actually need the answer to these problems. The 2 problems we see today, there will be real world analogs in which we actually care about this. The second problem will have a real world analog. The first problem I'm showing you just because it's like easy to understand. But the idea is twofold. One, we could try to understand the problem well enough such that we only solve the problems that we actually care about, the cases that we care about. So we take our initial problem, which is an NP complete problem. It's super hard. The algorithm that solves it completely in general will take O of, 2 to the n to solve at least, and that's really slow. Well, one way to deal with this is like maybe instead of solving the entire problem, we just solve a specific instance of that problem or a specific subset of the types of inputs you can put in. So one example is like, for example, for vertex cover, right? Minimum vertex cover. Normally we would have like general graphs that look like this, or maybe general graphs that look like this. But like you can think about it in such a way that, well, what if we just dealt with trees? If we just dealt with trees and just solved the problem for when we had trees, then, well, maybe it's easier to come up with an algorithm that solves it in linear time. For example, there are greedy algorithms that can find the minimum vertex cover in linear time if we only deal with trees, right? Which is a specific type of graphs. Now, we've actually done this in the past. We've actually seen examples of where we took a problem, made it a little bit easier, made it a little bit simpler, and as a result, we were able to come up with an efficient algorithm compared to what we would have had to do otherwise. I'll give you all about 30 seconds to think about it. Just go through the list of topics that we've covered. For example, we covered some stuff in sorting, we covered some stuff in trees, we covered some stuff in graphs. What algorithms do you know take advantage of simplifying the problem a little bit such that you can actually come up with a faster solution? So in other words, what algorithms do we already have we already covered that have that take advantage of simplifying the problem, right? So in other words, the first approach we had today for NP complete problems is to simplify the problem and only solve the simpler version, and maybe that's good enough. There are algorithms that we've seen that already do this, that we've already talked about, that basically take this approach. There's two algorithms in particular that I'm thinking about. All right, so let's just think. Go ahead and type in chat, question mark if you're not sure. Otherwise, give me your best guess of which algorithms you think I have in mind. Okay, we got a lot of question marks. People aren't quite sure. We see a few people with what the answers that I'm thinking of, and most of you are a little bit confused, which is totally fine. All the other sections had this too, so don't worry if you were a little bit confused. So the big idea here is like, okay, let's try to think about sorting. Sorting in general takes n log n. If you wanted to sort anything, like sorting metal bars, or sorting apples, or sorting cars, or sorting numbers, like it takes n log n for comparison-based sorting. But you can do radix sorting. Takes O of n because we assume that we're sorting numbers, right? We've simplified it and said instead of sorting any old thing, we could just sort numbers. And as a result, we are able to sort faster, right? Because radix sort takes O of d times n, where d is just a number of digits you have in each number, like the biggest number you have, what are the number of digits you have in there? And that's radix sort, which is effectively O of n, right? Because you never have a number with like a million digits or anything like that. It's very, very rare. And then like in general, if you wanted to sort just based on comparing two numbers against each other or two things, comparison-based sorts will take n log n instead, right? So one way that we've made a faster algorithm is by taking advantage of the fact that in sorting, when we're sorting numbers, there are some specific cases where sorting numbers is going to be faster than sorting in general. Could you use radix sort for sorting maybe the alphabet as well? Yeah, if you can convert the letters into some sort of number, that would work. Or if you can think about the radix in terms of letters, and whenever you have this concept of radix, then that would definitely work, right? The other example I was thinking about, which someone mentioned, I think, is actually Dijkstra's. What specific types of graphs do we need in order for Dijkstra's to work? Dijkstra's runs in O of v plus e times log of v, right? That was what Dijkstra's runtime was. What was the special rule on the graphs that we had for Dijkstra's that allowed this runtime to actually work and that Dijkstra's would always produce the correct answer for? Take 5 seconds. Punch it in chat if you have it. All right, go ahead and tell me. What do you think the special rule was? we needed to have positive edges, right? So edges that weren't negative and ideally not zero. Dijkstra's would work on those types of graphs, and we would get a really fast runtime. The alternative is Bellman-Ford, which was slower. It took O of V plus E, right? And that was, or sorry, O of V times E, which is fundamentally like a bit slower than what we have here, right? So if we had to deal with negative edges, that slows us down. If we have only positive edges, that allows us to use Dijkstra's, which is faster, right? And that's what it means to do number one. We're not going to cover number one in lecture since we've already looked at some past examples of this where we looked at algorithms that could be slightly faster because we took advantage of some part of the problem that we simplified or specified, fixed in some way. Now, okay, if we don't do that, and what does that leave us with? What is the other approach in which we deal with NP-complete problems? Well, instead of trying to find the best solution in order to find the optimal solution, so for example, trying to find the minimum vertex cover, why don't we find the vertex cover that's just simply good enough, right? One that just fundamentally will give us an okay answer, even though it's not the best possible answer. And this is generally good because it's faster to generate this, right? It's faster to come up with an okay answer, a good enough solution, instead of finding the absolute best. That's the hypothesis. And we're going to go ahead and look at that in our first example with minimum vertex cover. So if you remember from last week, and I keep talking about this, a vertex cover is a selection of nodes in a graph that touch every single edge in G, at least on one end, right? A minimum vertex cover is a graph, a set of edges, a set of nodes on a graph such that you have the smallest set of nodes possible in order to create this vertex cover. Right? So a minimum vertex cover is just a vertex cover, except we have the least number of nodes necessary in order to actually do the job. Solving this for all kinds of graphs is really expensive. The best algorithms we have are exponential. They take O of 2 to the n, as we saw in our exhaustive search lecture. Is there a way that we can pick up nodes and pick nodes in a way that's like just faster than what we had to do in exhaustive search that would give us a good enough vertex cover? And good enough in this case just means that it maybe isn't the minimum possible nodes we can choose, but maybe it's like, bounded in such a way that we don't have to worry about it too much. Someone mentioned, hey, can't we come up with a greedy algorithm to satisfy this? Yes, but there's actually an even easier way to look at this. So let's just remember how the minimum vertex cover works, right? Let's go ahead and remember that for a minimum vertex cover, pick nodes such that every edge is touched from at least one end. A minimum vertex cover is a vertex cover that has the least number of nodes needed to solve this problem, right? So in this case, I'll give you all about 30 seconds. If you're following along, what is the minimum number of nodes we need here, right? So my question here is, what's the minimum number of nodes needed in this case, in this graph here? All right, go ahead and type in chat. Question mark if you're not sure. Otherwise, give me your best guess. How many nodes do you think we need? All right, most of you are saying 4. Some of you are saying 3. So let's go ahead and take a look at one of the people who said 3. If we picked, for example, 1, 3, and 7, this is a problem because if you look at it, here are all the nodes that I've selected and all the edges that those cover. if you select those nodes, you don't actually cover some of these edges. This edge isn't covered, this edge isn't covered, and this edge isn't covered. So you're forced, in this case, to actually pick one more node. You're always forced to pick 4 in this example if you want to get all of the edges covered correctly. Right? So the minimum number in this case is going to be 4. And you have a couple of different options. You could do 1, 2, 4, and 6. I believe that would work. Sorry, 0, 2, 4, and 6. If we were to do that, that should be a minimum cover. Let me just stare at that. 0 would be this node, 2 would be these, 4 would be these, and then 6 would be these, right? So that would work well. You could also do, 1, 5, and 3 and 6. So 1, 3, 6 would also be fine. 1 is selected, 3 is selected, 5 is selected, and then 6 is selected here. You could also do, let me just type this out, 1, 3, 5, 6. You could also do 1, 3, 5, 7, right? These are all like reasonable minimum vertex covers for this node. And so we want to think about how we could come up with a solution that maybe doesn't give us the minimum here. So it maybe isn't 4, but will still get us a good enough solution, right? A solution that has a set of nodes that isn't too outrageous. If you just run the brute force algorithm here and you just kind of look down here, this is going to take a long time to finish. Like even if we sped this up, we can already just see on this bottom bar here that the progress is really slow compared to how we normally do. And so we need a better way. So here's an approach, right? Let's just imagine that I just came up with an approximation algorithm. That's kind of like the dumbest way I could do it, right? Here's a dumb approach. Why don't we just select edges, and then if those edges aren't, if the nodes attached to those edges aren't already selected, then add them. So what we're doing is select an edge. If those nodes that are attached to the edge aren't already in the vertex cover, add them to the vertex cover, and then remove any edges that those nodes touch. Repeat until we run out of edges to touch. All right, this is going to be my approach. This is going to be a lot faster than what we're doing right now with this, brute force, where it's trying out every possible combination. It's already found a good answer. It could have stopped a while back, but it's continuing to go because it's faithful to this, algorithm here, which doesn't try to quit early. Let's go ahead and look at a faster version, right? Actually, we'll wait for this to finish out of respect. All right, so this finally at the end will pick these 4 nodes, 0, 2, 4, 6. We're going to go ahead and just run this algorithm. All right, this algorithm, as I said here, we're just going to select an edge. We're going to select an edge in some arbitrary order. As always, when we have some arbitrary decision to make, we choose the smallest labeled nodes first. So the edge with the smallest labeled nodes here would be 0, 1. And as we said in this purple text here, we're going to add them to the vertex cover. In other words, I'm going to just check them off and say these are part of my vertex cover. For all the edges that these nodes touch, we're going to go ahead and gray them out. So the nodes that the edges that node 0 touches are now gray. The edges that node 1 touches are now gray. We're just removing them from the equation. All right, which means the next time we select an edge, we have to select an edge that's not gray, any of these edges that are still marked black. So if we're doing this again, if you're following along, what do you think is the next node we're going to go pick? I'm going to give you all about 10 seconds to think about it based on the rules that we have or the pseudocode down here. What do you think is going to be the nodes that we pick in order for this to work? What's the next edge that we have to pick? That's what I'm asking. Go ahead and type in chat if you have it. All right, we're getting a good deal of people typing in 2/3. And that's right, because what we're saying is of all the edges that aren't grayed out, pick one, any of them, but like since we have to tie break, we'll pick the one with the smallest labeled edges, which means 2, 3 gets picked next. So we'll mark those two nodes that are associated with the edge 2, 3 as part of our vertex cover. And then we're going to go ahead and just gray out all of the edges that 2 and 3 touch. In other words, 2, 5, 2, 3, and 2, 3, 6 are all grayed out now. Right? If we keep going, we're going to pick 4, 5 next, do the same process. And then finally, 6, 7. Now at this point, we've like selected literally all the edges, right? All of these edges got picked. That's not necessarily great. What's the best case? We said the best case was 4. If we select every single node, of course we're going to get a vertex cover. But how bad was it? Like in terms of how many nodes that we checked compared to our optimal, how many times worse was this compared to our optimal? Go ahead and type in chat if you have it. What's like the worst case approximation, or what's how bad is it compared to what we had here? If we had 4 here and we had 8 here, then how many times worse was it? Yeah, it's twice as worse, right? So note, approximation algorithm selected all of the nodes, right? All 8, which means that this was twice as bad as our optimum, right? So that's no good. That's kind of wasn't the best algorithm, right? Someone asked, hey, couldn't we use greedy here? I'm not going to explain why greedy doesn't work here, but there's like, right now, greedy won't make this problem any better. Greedy won't magically get us a situation where we can select and guarantee a better solution than at least twice as bad, right? So right now, our algorithm, we know at least produces on one graph a solution that's twice as bad. Let's go ahead and take a look at some maybe other examples that we might care about, right? So let's go ahead and take a look at this one. This one, we know that the best case scenario here isn't 4, it's 3. We can pick 3 nodes here. For example, we could pick 0, 1, 2, and that would be a valid minimum vertex cover. We could pick 0, 1, 2, 3. We could pick 2, 3, 4. These would all be vertex covers, and I think there might be a few more here. But like every time we pick a vertex cover, let's say we pick this one, 0 would touch these edges, 1 would touch these edges, and 2 would touch these edges. And it turns out you have to at least have 3 nodes. There's no other combinations where we could have like 2 nodes that would be able to touch every single edge. All right. So we know that the minimum vertex cover here will be one of these examples, or maybe even a different example that I haven't written down. But we know that no matter what, it's going to take 3 nodes. Okay. So if we were to try to run the approximation algorithm on it, in other words, do the thing in purple, what do you think the first node we'll pick will be? Go ahead and take 10 seconds to think about it, and then we'll all type it in together, right? I just want to make sure you really understand this algorithm. What is the first edge we're going to pick in order to get started on our approximation algorithm? So our approach here is going to be to pick some sort of node. Go ahead and punch it in chat if you have it. Right, so this time we're going to try this one more time, and maybe we'll get a better answer than what we did before. Okay, people are telling me to type in 0, 2. The edge 0, 2 is definitely going to be picked first. And this is interesting because if you look at 0, 2, they touch a lot of edges. So 0 will, and 2, these 2 nodes, all of these edges now will be marked gray so that we can just avoid picking these edges in the future, right? Which means that the next edge we pick will be either 1, 3 or 1, 4. Which one is it, chat? Okay, people are typing in 1, 3, and that's correct because we, again, between 2 edges that we don't have a real choice between, like they would be the same if we picked 1, 3 versus 1, 4. We just tie break by picking 1, 3 because it has the smaller label node. 1, 3 is smaller than 1, 4 in terms of comparing their nodes labels. So at this point, we go ahead and mark those edges as visited, and then we're done, right? And that's cool. That means that in this case, for our example, we actually picked the nodes 0, 1, 2, and 3. In other words, we picked 4 nodes. The approximate solution that we have here, the approximation algorithm gave me 4 nodes, which isn't bad, right? We didn't pick all of the nodes. We didn't pick all 5 nodes. We just picked 4. It's not as good as the best solution, but it's still not bad, right? We're still in good shape. Now is the time to think about, okay, is there a chance where the approximation algorithm will always produce like the best solution, or it will produce a solution that's as good as our best solution, right? So let's go ahead and look at one last example. In this case, we'll look at K5. It's called K5 because every single node has an edge to every other node. All right. So we're going to do this one more. What I want you to do at this point is to find the minimum vertex cover optimally. What is the optimal solution for this graph? And then we're going to run the algorithm and try to do it one more time using this approximation algorithm and see if it gives us a good answer, right? So I'll give you all about 30 seconds to just think about what is the minimum vertex cover for this graph. And then we'll look at it together. All right, how many nodes will we need in order to get our minimum vertex cover? We need how many nodes? Okay, people are typing in 4 nodes. Interesting. Well, okay, let's go ahead and think about it. If we were to try to pick 3 nodes here, it's not going to work because let's say we pick 0, right? These are all the same, like every node has the same number of edges going out. So you can start at any arbitrary node. If we pick this node, we would select these edges. If we were to pick another node in order to complete this vertex cover, for example, 3, we would get these edges. And the problem here is that at any other, like for any of the other nodes, no matter which node we pick, we'll end up missing one more edge here. So for example, if I picked 1 here, I could get these edges selected, but then I would still need the 2, 4 edge, which, you know, can only be picked if we picked either 2 or 4 as part of it, right? So in this case, we need 4 nodes, which means our minimum vertex cover might look like 1, 2, 3, 4. Sorry, yeah, it could be 1, 2, 3, 4. It could be 0, 1, 2, 3 as well. It could be, you know, 2, 3, 4, 0. It really doesn't matter, right? So there's a bunch of these different combinations, any combination of 4 unique elements here. Now, if we were to do this one more time with the greedy approach, in this case, I'll give you all 30 seconds. What are the nodes that we pick? What are the nodes that we pick with not the greedy approach, the approximation algorithm? Sorry, this is not a greedy algorithm. So in other words, we run this stuff in pink here that I've written down. What are the nodes that we're going to pick based on that? What are the 2 edges that we're going to select at the beginning? And will we have to select more edges after that? Give you some time to think about it. I just want the 4 nodes that this approximation algorithm is going to output. All right, what do you think? Go ahead and let me know. What do you think the nodes picked based on the algorithm is? Right, let's just go ahead and run it. People are telling me some good answers in chat. If we run this one step at a time, we know at the very beginning, the first edge we're gonna pick is gonna be the 0, 1 edge because we don't know anything. 0, 1 edge covers all of these edges in blue, right? That's a lot of edges. And as a result, all of those get grayed out, and only the edges here marked in this triangle here between 2, 3, and 4 are selected, are selectable. We'll pick 2, 3 because that's the smallest labeled edge, and then we'll just wrap it up and then we're done, right? So in other words, we pick 0, 1, 2, 3 as our approximation solution, which is exactly the solution that we sketched out when we were trying to find the optimal anyway. So in this case, the approximation solution, it turns out, has a good answer, right? So in the worst case, what we found out, right? Let's go ahead and write down our observations based on these examples. In the worst case, the approximation algorithm produces a solution that's 2 times worse than the optimum. In the best case, it produces the optimum solution, right? That's what we found out so far. Now, there's a couple of things we need to actually think about in order to make sure we understand this correctly. So first thing we need to think about, let's just answer these 3 questions. 1, are we sure this algorithm will always produce a valid vertex cover? In other words, does this always work? 2, what's the runtime? Like, is this actually fast enough to be considered an approximation algorithm? Because again, we don't want this to run in exponential time. That would be just as bad as what we had before. And 3, how bad could our approximate solution get in the very worst case, right? Is there a way to prove using math or logic that the worst case scenario is that it'll always be 2 times as bad and no more, right? It could never be 3 times as bad is what we're hoping. Well, the answer for 1 is relatively straightforward. Let me just sketch it out, right? We know that we're picking edges and adding the nodes into our vertex cover, right? That's what we have so far. Every time we add nodes, we remove edges based on the nodes that based on the edges they touch, right? So when we started here in this example, at the very, very beginning, we picked 0, 1 as our edge, and then we removed all of these edges in blue, right? So in other words, we pick nodes until we're out of edges to pick. We remove edges to pick every time we select 2 nodes that add into our vertex cover. Therefore, we only end after we run out of edges, which implies that we've touched each edge, right? So we're picking nodes until we run out of edges to pick. That's just generally the algorithm that we're doing, right? In purple here, or pink, however you want to interpret this color. We remove edges from consideration every time we select 2 nodes that add to our vertex cover, right? All of the ones in blue right now are selected. Therefore, we only end after we run out of edges, and we only run out of edges because we've actually selected the nodes that those edges are already attached to, right? So we are guaranteed a vertex cover by going through this algorithm, right? Because the only time we stop is when we run out of edges, and we are only removing edges and making it smaller and smaller until we run out of edges to consider in this loop here. When we are selecting nodes that touch those edges, all right? You see what I've highlighted here in black in the pseudocode here. Take both vertices and remove incident edges. That's what we're doing here, all right? Now, if we keep going and we ask what the runtime is, we have to think about it in terms of the code that we have here, right? So like, let's just think. We have to go through every single edge in the worst case, right? How many, if we were to put this in terms of V and E, where V is equal to the number of nodes and E is equal to the number of edges, in the worst case, how many times do we have to iterate through this for each loop here? This should really be a while loop where, while we still have edges left to consider, that's really what we're asking. How many times do we have to iterate through in the worst case? Go ahead and type in chat if you have it. Right, a lot of people in chat are typing in E. So in the absolute worst case, we'll need to iterate through the for loop E times, right? So for whatever reason, all of the edges are kind of stuck on their own. And so we need to iterate through this E times. One example of that might look like this. Yeah, this one. Right, so we have to iterate through every single edge here no matter what, and we're not removing anything here. Now, if we are thinking about it carefully, the inner for loop is not actually going to take any extra time that is scary here. Mostly constant in the iteration every time we iterate through. Removing incident edges will be in total O of E for every single iteration, right? So this is just a fancy way of saying, hey, if I remove edges that these nodes are touching, then that means we're going to remove at most E nodes, right? Through every single, if we count through every single iteration of the for loop, right? Which means that the overall runtime here, O of E, because we literally just go through every single edge and we're removing every edge, once. And we're iterating through each edge once in the worst case. And therefore, the overall runtime would be something like O of E, which is way better than what we had before. If you remember, brute force solution to get the optimal solution, brute force algorithm to get the optimal solution was O of 2 to the n, where n is equal to the number of edges, number of nodes we have. Right, because we have to generate all possible subsets of the nodes in the graph from last week, and that was 2 to the n, right? If you don't remember, then just believe me. It was actually something like O of E times O of E times 2 to the power of V, I think was what I decided on, which is kind of terrible. And actually, it's properly terrible, right? It's exponential time with respect to the number of nodes in the graph versus linear time with respect to the number of edges. So we know that this is at least fast, right? Lastly, how bad could our approximate algorithm get in the very first case, in the very worst case? We know for now that in the worst case, it seems like our approximation algorithm will produce a solution that's 2 times worse than the optimum. And then in the best case, it's going to give the optimum solution, all right? Let's go ahead and just try to think about why that's the case. In this case, if we just run our approximation solution, let me make this faster. All right. Think about it this way. All right, I'm going to sketch out the argument for why we're guaranteed that 2 times is as bad as we get. Like the answer that we came up with due to looking at some examples is actually the right and final answer, that this algorithm will produce an answer that is no worse than 2 times worse than the optimal solution. In other words, if we had an optimal solution, let's just imagine OPT of I is equal to the optimal vertex cover, the minimum vertex cover for graph I. Well, that means 2 lines around it is equal to the total number of nodes we need for a minimum vertex cover. Let's just imagine now that our approximation algorithm is going to be equal to 2. How do I describe this? We're going to have this thing called M, which is the edges we picked when coming up with the approximate solution. All right. Type in M if you're with me so far. So we have this symbol here, which is just the vertex cover for I, the minimum vertex cover for some graph. This is the total number of nodes we need for a minimum vertex cover, which is what we had before, just with 2 lines around it, because this is the set of nodes and this is the number of nodes in that set. Now, M is just going to be the edges we picked whenever we ran this algorithm. All right. Why do we care about this? Well, it turns out there's a relationship. We know that the number of nodes we need in the best vertex cover, in the minimum vertex cover, is actually going to be greater than or equal to the number of edges we're going to pick in this algorithm. Because if you think about it, when we pick edges in this algorithm, we're always picking edges that don't overlap with other nodes, right? So the observation I need you to make is that we're always picking edges such that we don't overlap in the nodes that we select. Okay, let's just go back to one of the examples on the smaller graph. We had this graph. When we ran the approximation solution, what we did was we picked 0, 2 first, and then we picked 3, 1. In other words, 0, 2, this edge has no nodes that are shared with the other node that the other edge that we picked, which is 1, 3. And if you think about it carefully, that means that the number of edges we pick will always be either less than or equal to the number of nodes we have in the minimum vertex cover for graph I. All right. It's not obvious why. You're going to have to think about it carefully. I'll post some video or some like paper for you to read in order if you're like super curious and dying to know. But for now, let's just assume that this is true. All right. Well, okay. This is M, which is the edges that we picked. If we picked M edges, how many nodes did we actually pick in the vertex cover for our solution? I'll give you 15 seconds. If you feel like you're following along, you should be able to get this answer. How many nodes did we pick if we picked M edges for our approximate solution? All right, give me an answer in chat. Question mark if you're not sure. Otherwise, give me your best guess. Okay, everyone's confused. Some people will get it. One person gets it. Everyone else is confused. People are saying M plus 1. Remember, M is the number of edges we picked. Every time we pick an edge, how many nodes do we touch? Go ahead. What do you think, chat? 2, right? So if we pick M edges with 2 lines in around it, then we actually picked 2 times M nodes, right? The number of nodes we picked is twice the number of edges because every edge touches exactly 2 nodes and none of the nodes overlap with each other, right? As I just said, we always picking edges so that the edges don't overlap with any of these shared nodes, which means that if we multiply both sides here with 2, then we're saying that 2 times the optimum solution is going to be the bound for the number of nodes that we picked. So this is the number of nodes we picked, and this is how it compares to the best, the optimal solution, right? It's twice, at worst, it's twice the optimal solution. So the observation, the part that like you need to keep in your head is that whenever we're picking edges, the way this algorithm has us working is always picking edges that don't have nodes that overlap with the previous nodes that we selected. And that's how we're able to say, okay, well, then like the number of nodes we have in our best minimum vertex cover is going to be greater than or equal to the number of edges we pick. All right. And that means that the number of nodes we pick in our approximate solution will always be no worse than twice the optimum number of nodes we need. All right, that was a lot to take in. Let's take a 5-minute break. We'll come back at 6:50. Let's just go ahead and chill for a little bit. I love this image. It makes me really happy. I wish all of my break time slides were as beautiful as this image. I really love Calvin and Hobbes. But if you're stuck with any of the stuff that we just talked about, please let me know. I'm happy to answer. Otherwise, just take a break, get some water, stretch, and we'll come back in about 4 minutes now. When is our final exam? Not next week, but the week afterwards. It's going to be the week of the 26th. And for the Monday, Wednesday section, they'll take their exam on the 26th at the normal time. And then for the Tuesday, Thursday sections, they'll take it on Tuesday at the normal time. So for this section right now, Tuesday, Thursday, 5:30 to 7:15, we'll take it at 5:30 on the 27th. I'll make a post about this pretty soon. I know some people are trying to plan out their final exams schedule. So it will be on the 27th for you all. Can I explain the 2M part again? By the way, you can go to any lecture you want for the final exam. So if you have two hard exams on the 27th, like my exam and someone else's exam, then you can come to the Monday exam if that will make you feel less stressed. I don't know if it will make you feel less stressed, but at least you can spread out the pain. It's totally up to you. I'll, again, post on Piazza by the end of this week about the rules for the exam and what to expect. Can I explain the 2M part again? So 2M is the number of nodes we select in our approximate solution, because we define M as the edges we picked whenever we ran this algorithm. And so if this is the number of edges we have, 2 lines around this M, that's the number of edges we have, then 2 times M is the number of nodes we picked, right? So this here is defined as the number of nodes in our approximate solution. And what we have on the left-hand side is just some math. We said 2 times the number of nodes we have in our optimum solution. So this math expression on the very end here says, the number of nodes you're going to pick in our approximate solution will be always less than or equal than 2 times the optimal number of nodes you need. All right. We still have a minute to chill. Hope you are all having a good April so far. How's the semester looking? I got a vibe from last section that there was a lot of people still feeling like there's a lot of semester left. For me, I'm feeling like this is getting close to the end of the semester. I'm like eyeing all the exam grading that I'm gonna have to do and all the grading we have left for your homeworks and quizzes. But I get the sense that a lot of people don't feel like it's the end of the semester yet. So happy that it's almost over. I thought we were done. I mean, we're done in this class. I'm just asking in general for like the semester. Remember, we still have lecture next week, and you'll want to come to it because it's going to be really valuable for you for preparing for the exam. We're literally just going to go through some exam exercises, and the answers to the exam exercises will be part of a review assignment that you're going to want to turn in for corrections anyways. All right. Let's actually just double check here. Week 14 announcements. So announcements for this week. Homework is due tomorrow. It's just reading something really quick and answering questions in a short Google form. Check the link on the website if you haven't already. Should be straightforward. If you missed this assignment by not doing it, it is 100% on you. This is a short article to read about how to take care of yourself mentally. And then I'm just asking you some questions to have you reflect on how you're feeling this semester. Quiz 10 you just took, so let's skip that. Final course survey is out. So you were emailed this out, and it's an anonymous survey to ask you, hey, how are you doing in this class? How are you feeling about the topics? Are you feeling like you're learning? Is there anything that you really like about this class? Is there anything you feel like we could be doing better? Always feel free to share with us. It's anonymous so that you can share. There's no way I can trace who said what. And I'll always look at this to use the data that we get, the feedback we get to improve the class. So please fill this out if you can. I really, really appreciate the people who fill it out. Even if you feel like this class isn't going well for you or that there's something about this class that you wish were different, I really appreciate that feedback. It helps us make the course better, and it helps me learn how to be a better teacher, right? Because I'm not perfect and there's a lot of things I can still improve on. And your advice and your feedback lets me know. Exam 2 stats are out. There are advice that you can learn from here about what you can do to make points back. So for example, the homework corrections are still you can still turn them in for less points. The homework recovery, the exam recovery will come out soon. Homework 9 was out, and there's going to be a review assignment, as I mentioned, for exam 3. Right. And then doing well on exam 3 yourself, of course, will bring up your grade. It's worth 15% of your grade, so you should do your best. Corrections are defined here. If you have any questions around them, let me know, and we will do our best to help. But basically, you should go through all of your answers for the exam and then fill out this spreadsheet, or not the spreadsheet, but this form, such that you are able to tell me for each problem, what score did you get based on the rubric? Why did you miss points if you did miss points? Give me some details on why you think you missed points and what you're going to do differently next time. And then for quiz recovery, in order to get some points back on the quiz, you can tell me what lecture and slide number it came from, or what timestamp it came from a video in that this question tested. What about corrections for 5 through 8? I answered that on Piazza, but basically 5 and 6 we'll do corrections for next week. 8 and 7 will be based on the exam review assignment that I'll release next week. Right? Like we 100% want you to be able to max out your quiz scores and max out your homework scores. So I'm trying to make it so that you have an opportunity to do so. All right. Let's come back. Let's take a deep breath. We got 20 minutes. We're going to go ahead and cover the last topics that we care about. In this case, we're going to cover approximation algorithms, give the formal definition, and look at one more approximation algorithm. Go ahead and type blue in chat if you're ready to learn again. Take a deep breath with me. All right, let's start. Approximation algorithms, as we saw, solve NP-complete optimization problems in polynomial time by producing answers that aren't actually that good, right? They're sometimes optimal, but most of the time they're good enough. These algorithms are oftentimes easier to understand and easier to write, right? And that's the example we saw here. We saw that this wasn't super hard to like come up with, and if you had to code it, it wouldn't be the end of the world. It wouldn't be super difficult to code this out. But the runtime is very good. Sometimes it gives us a good answer, and we know that at worst, it's going to give us 2 times the optimum answer, right? Whatever the optimal number of nodes we would have, we would select at worst twice the optimal of the number of nodes the optimal answer has. Now, how good an approximation algorithm is measured by how far away the solution is compared to the optimal solution. Right. So this is just a fancy way of saying that if we had a 1.5 approximation algorithm, that means that we'll always generate a solution that's no worse than 1.5 the optimal. For this algorithm here, this was a 2 times approximation algorithm. So this was a 2 approximation algorithm. Right. This is why it says 2 OPT. Every time we run this algorithm, we are guaranteed that this will be no worse than twice the number of nodes that we would need compared to the optimal solution. Now we're going to look at another one of those, another 2 approximation algorithm for the traveling salesman problem. All right. So example number 2 is for the traveling salesman problem. Mathematically, this makes sense, but surely a lot of the time it runs 4 or 5 times the optimal. Well, I'm saying that the solution you get from running this approximation algorithm, for all approximation algorithms, it's bounded. Like approximation algorithms are useful when they're bounded by some number of how bad will this solution be compared to the optimal solution. Most approximation algorithms that are useful are no worse than 2 times as bad. There is actually an approximation algorithm for the traveling salesman problem, which we won't look at, but that you can learn about later. That's 1.5 compared to the optimal solution, which is pretty good. Can I show the blue slide again? This is a blue slide. I think I shared the slides with you in chat, but I'll do it one more time in case you want to skip around or go back to what we needed to look at. Let's go ahead and talk about traveling salesman. Traveling salesman is this problem where you have a trip you're planning. You're a salesman. You have in different cities that you're planning a business trip. You decide to start in the city you're currently in, let's say Atlanta, and you're going to visit all around the country through n minus 1 other cities and then come back to Atlanta when you're done. So you want a round trip and you want to visit every other city exactly one time, and you want to minimize the total distance that you travel, right? That's the aim of the game. So the input might be a list of cities and a cost function between any two cities. In other words, it's a graph where every single edge is defined with some weight which describes how far away city A is from city B for all pairs of cities inside of my graph. And the output is going to be an optimal tour. In other words, a trip around all n cities so that the city you start with is the city you end at. And the total cost to visit all of the cities is the best possible cost you could generate compared to all other trips you could have taken. Now, you might wonder, like, why do we even care about this, right? Like, why is it that we would care about this, even if it's such, like, since it's such a hard problem, why don't we just ignore it? Well, think about how we do deliveries in the United States and in general, right? There is some, FedEx shop, a FedEx warehouse with all of your packages that came from all around the world to the Atlanta area. A FedEx driver will get into his or her truck in the FedEx building, pick up all the packages, and then drive around to n minus 1 other locations dropping off packages. And then eventually they're going to have to go back to the FedEx shop, the FedEx building, to either pick up more packages or in for the night, park the car, and then go away, right? Like go home. So think about how many packages we go through every day. Think about how many different locations those FedEx drivers have to visit. You have to literally, like, if you minimize the amount of distance they have to drive, that's time saved for that person, that's money saved and gas saved, and the car will have to drive less distance, so the car will save, we'll be able to use that FedEx van longer. So any improvement to this pathing problem will fundamentally improve shipping, which is such a big part of our lives right now that it would save everyone a lot of time and effort, right? Your packages are cheaper to get to you, which means you'll save on shipping costs. The people who are doing the work will take less time to do their jobs or be able to get more of their job done in fewer trips. And overall, we're just saving costs in terms of the resources used, right? Same thing for Uber Eats. Like you start at maybe a restaurant, you go around and you visit everyone, and then maybe you go back to that restaurant for like the second set of orders, right? If you always visit the same McDonald's or something like that. Okay, so let's go ahead and take a look at an example. I'm going to give you all 1 minute to stare at this graph. You have, in this case, 5 cities, A, B, C, D, and E. And what we want to do is find the optimal tour. In other words, if we start at A, where do we want to go next? Let's say we want to go to B next, or we want to go to D next, right? All of those are possible. Where would we want to go from there? And how would we find the minimum tour? The minimum tour is the cost to go from A to every other node back to A that minimizes the total cost along the edges. Yeah, we start from A and end at A. So check the pink or the purple text for more context here. So I just want you to see if you can find the optimal tour here. All right, question mark if you're not sure. Otherwise, give me your best guess. What do you think? All right, so people are saying, let's go from A to D, and maybe then D to B, B to E, E to C, and then C back to A, right? That's a path. So one possible combination of events is that we could go from A to D to B to E, E to C to A, right? And if we add that up, I believe what we get is 5, 10 costs total, right? Can anyone find a cost that's cheaper than that? I think I saw an 8 in there. Did anyone come up with a scenario where we ended up with a smaller loop from A to A that costs less than 10? I'll give you all 15 seconds to see if you can spot one. It might exist, it might not. I'm pretty sure this is the best, but I'm not 100% sure. All the previous sections said that 10 was the best we could do. Type in best if you think this is the best. Otherwise, give me an answer of what you think could actually be better. There are multiple that tie for 10, but what I want is whether or not there's actually a better one than what we have here. Okay, most people are saying this is, can we visit a node more than once? For the traveling salesman problem, no. In general, we don't want to visit a node more than once unless it's the node that we started in. So we can visit A in that A, but that's it. Okay, most people are saying this is probably the best, and I think so too. So the problem, of course, is that finding this in general is really hard. Like, in order to find the answer to the traveling salesman problem, the best solution we have so far is a dynamic programming algorithm that takes O of n squared times 2 to the n. So this is kind of like dicey. Someone said A, C, E, B, D, A. Well, that's the same path except in reverse. That just gives you 10 again, I think. I don't know. We'll play around with it in a second. But the idea that we have right now is like, okay, instead of trying to find a tour that's the best possible tour, the one that's the cheapest cost, let's just find one that has a small cost in general and just be done with it, right? How would we do that? I don't expect anyone to know off the top of their head, but what are some graph algorithms that have to do with cost and distance? What are some cost algorithms that we have? Go ahead and type in chat. You should be able to list at least a few of them, right? What are some? Okay, Dijkstra's. Everyone's typing in Dijkstra's so far. That's fine. Are there any others besides Dijkstra's? Bellman, that's good too. So Bellman Ford also is something that we've seen. Anything else that has to do with edge weights on a graph? Kruskal's, very good. So Kruskal's is another example. Topological sort doesn't have to do with edges at all. Or sorry, it doesn't have to do with weighted edges. So topological sort does have to do with graphs, directed acyclic graphs, but there doesn't need to be edge weights. Prims as well. Nice. So the kind of tricky, or the kind of the trick here is we can just solve this using minimum spanning trees. Right? If you think about it, a minimum spanning tree is on a graph is just a set of edges that we pick so that every single edge is touching every single node, right? Or let me try that again. A minimum spanning tree is a collection of edges that touch every single node at least once. And it minimizes the total amount of cost by selecting those edges, right? So let's just go ahead and try this. Let's go ahead and try the minimum spanning tree. What we had before was the best tour. The best tour looked like this, right? So what we could say is that the OPT, the optimal instance here is this. This is one example. Now, what if we wanted to do the minimum spanning tree of this, right? Let's just go ahead and try to find the minimum spanning tree, which is a different kind of problem. If we were to do this using Kruskal's, which is just repeatedly picking the smallest nodes over and over again, we'll just go ahead and pick, like, for example, AD, because that's the cheapest node, right? Like AD is really, really cheap. It has a cost of 1. We'll pick that, include that in our minimum spanning tree. What's the next node we would pick here? Go ahead and type in chat if you have it. What's the next edge? Edge we would pick in order to kind of continue this. It would be AB, because that's the next node with cost 2. And AB is the smallest of all of the nodes, all of the edges with cost 2. So we would pick that next. AC is afterwards, right? And then we would try to do, in this case, BD, but that would create a loop. So we actually don't. And then we would do BE. All right, so this would be our minimum spanning tree. What's the cost here? AD gets picked, AB gets picked, AC gets picked, and then BE gets picked. What's the cost that we have here? If we just add up all the weights here, right? This is a minimum spanning tree because it has the cheapest possible edges necessary in order to pick this up, right? Okay. Okay, how does that help, right? Like that doesn't give us a tour. We don't go from A and then end at A. Here's the trick. We're going to go ahead and try to visit every single part of the nodes that we care about. So let's try to go from A to B, B to E, and then go back from E to B, and then B to A, right? In this case, we visited nodes twice, which is a little bit dicey, but I'll fix that in a second. And the next thing we'll do is we'll go to C and then back again, right? And then we'll go to D and then back again. All right. If you're following along, we know that this isn't a tour. We know that this is not the same as solving the traveling salesman problem. But what would be the cost here if we did this? What if we pathed and did this? We went from A to B to E to B to A to C to A to D to A. What would be the cost here? All right, people are typing in 14 in chat, which is correct, right? Because all you're doing is you're doubling the edges. Every time you have an edge, you use it twice. So now we have some sort of possible solution, which is this thing. Well, this is a problem, right? As I mentioned before, we can't really do this because we can't visit every single node twice. We can't visit B twice. We can't visit E twice. We can't visit A like 4 different times. We can't visit B twice. We visit E here. This should be a D. We should visit E once. We visit D once. We visit C once. That's great. So how can we actually just cut this up? Fix the doubling back by cutting across. What I mean by that is instead of going from A to B to E and then back to B and then back to A in order to get to C, what we're going to do is just cut out the middle person, the middle cities, and go directly, in this case, to C. Instead of going from A to B to E and then back, we'll go from A to B to E and then go directly to C. And then instead of going from C back to A in order to get to D, we're going to go from C directly to D. And then we'll go back to A. In other words, we'll cut out any of the repeats. We'll cut out the repeats here. We know that we went from A to B to E. Now, instead of going back to B and A, we're going to cut these parts out and go directly to C. Instead of going back to A, we're going to cut that out and go back to D, and then we'll end up at A. So our approximation will be this. Hey, what's the cost here? We have 2, 4, 7, 9, 10. The cost is exactly the cost we had in our optimal solution here. Neat. Right? So let me just summarize what we just did. We went and found the minimum spanning tree of this graph. The edges we picked, we're going to actually use. And the way we're using it is that we're going to go at the beginning and just kind of trace through every single edge and then double back to A over and over again. And then in order to make this an actual tour, in other words, in order to avoid visiting the same node multiple times, because that's not allowed in this tour, we're just going to cut through to the next city. So instead of going from A to B to E, and then back to B, and then back to A in order to get to C, and then go back to A, and then go to D, and then go back to A, we go A to B to E, and then go directly to C, go directly to D, and then go back to A. This works because of a neat little property called the metric property. The fact that an inequality, the triangle inequality holds, is also another way to think about it. In other words, the shortest path between two cities is a straight line, right? It's a straight shot. Going from E to C will always be cheaper than going from E to B to A to C, right? The cost for me to go from San Francisco to Atlanta, the distance traveled, will be cheapest. There's no way that, for example, I could go from San Francisco to Michigan, or like, what's this? Michigan's a state, right? What's a city? I don't know. Let's say I went to Chicago. I went from San Francisco to Chicago and then Chicago to Atlanta. That's going to take longer than going from San Francisco to Atlanta directly, right? And that's what we're saying here. We're allowed to do this weird cutting thing where we avoid going back to B and A, or avoid going back to A in order to get to D, because we know that the distance will always be smaller than what we currently have. Right? The current cost that we had was 14, and we brought that back down to 10 because we could skip a few steps. And we could skip a few steps because of the way that, physical space works. Going in a straight line is always going to be faster than taking a detour. Okay, lastly, let's just think about how this is compared to the optimal solution. Now, this example here was really good, right? We happened to have the best solution coming out of this, and that was lucky. I picked a graph that happened to illustrate this point. But in general, we're not actually going to be that lucky. In general, this is actually going to be kind of dicey because if you think about it, we have some sort of optimal solution, right? The optimal tour here, this is the cost of the optimal tour. It's going to be greater than or equal to the cost of the optimal tour minus one edge. In other words, let's say this was the optimal tour, which it is an example of it, right? And the cost of the optimal tour is going to be 10. If I remove any edge here, it doesn't matter which one edge I remove, we're going to end up with a cost that's going to be cheaper than that, right? By whatever that edge is, because all the edges are going to be positive because we're talking about real world cities. Now, the thing is, when we have a loop and we take out one edge, this becomes a spanning tree. This is a spanning tree now, right? Just think carefully about it. A spanning tree is a set of edges that touch every single node at least once, right? And there are no cycles in it. So if we took what was a cycle and we removed an edge, now we have a spanning tree. Now, this spanning tree, it could be the minimum spanning tree, or it could be worse than the minimum spanning tree. We know that the cost is at best equal to the minimum spanning tree, but worse than that would be like more, right? Like, so if we take the optimal tour, we remove any arbitrary edge, we're going to have a spanning tree that's going to be either equal in cost or more than the optimal minimum spanning tree. Well, if that's the case, that means we have a relationship. We know that the optimal tour, the cost of the optimum, is going to be less than or equal to the optimum, the best MST of I. Now, we used every edge twice, right? In our possible approach, we just doubled the usage, which means that the cost here is double as well. So our best solution, our approximate solution, which is described by this cost, is always going to be less than or equal to twice the optimum. All right. That was the kicker. So this is also a 2 approximation for the traveling salesman. Since we use every edge twice, right? We don't really use it. We do cut across sometimes, but that only make our costs cheaper. We know that at most, our solution is going to be 2 times worse than the optimal tour. All right. One last thing. The cost here, the runtime of this algorithm, is going to be how much it takes to find the minimum spanning tree, which I believe, if we remember correctly, is O of E times log of V, right? Which is cheaper than some exponential time algorithm, which we hinted at for traveling salesmen. So this is cheaper. The time it takes to go through and find the minimum spanning tree, plus the time that it'll take to kind of cut across all of the edges, which will be another order of O of V, and we don't really care about that. So the runtime overall of this approximation algorithm is the same as finding the minimum spanning tree. So we're able to change the code for the min-c to cut across the nodes pretty easily. Yeah, because if you just see this, we just take these nodes that we have here, and then we just skip the ones that we see repeats of. So we just literally go from left to right in this pathing, and then we just skip any duplicates, which would be linear time to do. Right? So the runtime of this algorithm is also polynomial, right? Because this approximation algorithm is supposed to be cheap and give us an approximation that is good enough. Okay, so when we are considering optimal solutions, NP-complete problems, only have exponential algorithms that solve the problem, right? In other words, we're screwed if we're trying to find the best solution every single time. Approximation algorithms give up on that, try to find the optimal solution, and instead find one that's good enough. Minimum vertex cover and traveling salesman are both NP complete. They both have algorithms that are at most 2 times the optimal solution. And for decades, actually, for traveling salesman, the best we could do for traveling salesman was 1.5 times the optimal tour, the best approximation algorithm we had for that. And very recently, like literally last year, they came up with an algorithm that actually beats that slightly. So the best case now is slightly better than 1.5, the optimal solution for our approximation algorithm for traveling salesmen. If you want, you can read this article. It's very neat. It isn't too technical, so you can definitely follow along. If you haven't already, please, please, please read the announcements and everything that's listed here, especially the advice on how to boost your grade. I think that's really important for those of you who are stressed out and want to get the best grade you can. That's all we have for today. Thank you so much for your time. Come back next week and we'll study for the exam together. Thank you very much. Have a good weekend. If you have any questions or concerns, I'll be here. We're in office hours. All right. Take care, everyone.